The double-layer spherical capacitor with foil. There are two conductors, solid sphere inside and the hollow sphere outside. Between spheres there are two layers of dielectric media with different dielectric permittivity, epsilon 1 and epsilon 2. Dielectric layers are separated by the thin conducting foil. Our task is to calculate capacitance between spheres. In fact, the foil divides the capacitor into two capacitors. And here you can see the analytical solution to calculate the capacitance of each of the capacitors. We will simulate this case in QuickField and compare our results against the analytical solution. The capacitance is the ratio of the charge to the potential difference, and I'm going to assign positive potential to the foil and zero potentials to the spheres. And then I will use QuickField to calculate electric field distribution and the charge values. So I start QuickField now, and in QuickField I create new problem. The problem name is sphere foil sphere. Next. The problem type is Electrostatics and the model class is three-dimensional import. Length units are millimeters. Okay. Here on the left you can see the problem tree, and on the right you can see the geometry model editor window, and I will import the geometry model from the step file. Step file is used to exchange geometric objects between CAD system. So open. So we have three bodies here, but I can see only one. I will make the bodies transparent so that you can see what we have inside. Select, right click, transparent. We have internal conducting sphere, and we have two layers of dielectric media. We do not have external hollow sphere here, but in fact we do not need it. There is no electric field inside massive conductors. It is enough to include the conductor surface. To distinguish geometric objects from one another, we can assign labels. And through labels we also provide physical properties. To assign a label to geometric object, we should select the object. And to select the object, you should click it. I will make all objects opaque again, so you can see better when the object is selected. Now I move the mouse over the object is highlighted, and I click it. The color has changed and the object is selected. What is selected you can see in the properties pane on the left, and you can see that the face is selected. Well, that would be the inner surface of the outer grounded sphere. So I type in the label name here, grounded. And you can see that the label appeared in the problem tree. Now if I select the label in the tree, the corresponding geometric object will be selected. And I can assign physical properties to the label. Double click it and type in the electric potential value 0. To select the body, I should click the selected face again. Now you see the selection color has changed, and in the property pane I can see that the body is selected. That is dielectric epsilon 2. So I type here epsilon 2. If I double click the label, I can specify relative electric permittivity, which is 2. To see internal objects, I will hide this dielectric layer. Right click, hide. I can click and select the face which represents the foil. So I give it the name foil. The foil has electric potential of +1 volt. Click again and select the internal layer of the dielectric. That is epsilon 1, and this dielectric features relative electric permittivity of 6. Okay. Again, I will hide the body, and now we can see the internal sphere. I click and select the face, and this face is grounded, so I select the face label grounded. And if I click again, I will select the internal sphere body. But there is no electric field inside massive conductor, so there is no need to assign label and physical properties. So I do not assign label here. Now let's unhide everything and verify the labels assignment. I will use cut by plane to see the inner structure. Now I will click the label foil. You see the foil layer is selected. Now I will click the label grounded. The internal and external sphere surfaces are grounded. Epsilon 1 is the internal layer of the dielectric. Epsilon 2 is the external layer of the dielectric medium. The model looks alright. Next we should build the finite element mesh. Just click the button and the mesh is ready. That is fully automatic mesh, and you may see that the finite elements are too large. Instead of the smooth curved face of the sphere, we have sharp corners, and the field distribution might be inaccurate. If you do not like the automatic mesh, you can adjust the mesh density manually. The mesh is generated in 3 stages. First, the edges are subdivided. Then faces. If you look inside, you will see that only faces has the mesh now. And the last steps is volume meshing. So the meshing starts with edges, and you can attenuate the mesh in the edge vertices. Here is the edge, and I have selected the single vertex of this edge. The spacing value in this vertex is automatic and set to be 50 millimeters. I can change the spacing to manual and type in some other value, for example 20 millimeters. Now, how can I distinguish vertices where manual spacing is specified? You can use the spacing button. Manual spacing value is visualized using the spheres around the vertices. You see, in this sphere we have specified manual spacing, but in this vertex the spacing is still automatic. I can select this vertex and change the spacing from automatic to manual and type in, for example, 50. You can see that the meshing step is different along this edge. It changes from 20 millimeters here in this vertex to 50 millimeters at this vertex. Surface mesh will follow this pattern. Large triangle elements here, small triangle elements here. The volume mesh will follow this pattern too. But if you look inside, you will see that the mesh elements are still there. That's because we haven't assigned spacing for the inner spheres. Inner spheres has automatic mesh spacing, and QuickField decides that such elements are good enough to build the mesh in the internal objects. Well, you can select the vertices of the inner objects and adjust the mesh spacing there individually. But in this particular geometry model, I would like to assign the same manual spacing for all objects. I will select all objects, switch spacing to manual, and type in the spacing value to be 20 millimeters. Now we can build the finite element mesh on surfaces in volumes and run the analysis. Press solve button. Yes. And we can see the results now. Here we can see the electric potential distribution along the hollow sphere internal surface. And the electric potential is 0 everywhere as we have defined it. To look inside, again, I can hide elements or I can use the cut by plane tool. Now you can see the electric potential distribution inside. My task was to calculate capacitance, and there are two ways you can do this: from energy or from charge. Capacitance is charge divided by the potential difference, which is 1. And the capacitance is double energy divided by the potential difference squared. Both approaches should provide the same results. Now let's see. I select the internal dielectric layer, and the energy is follow to the integral stored energy. Let me copy the picture and the results in the Word document. That's the picture, and that's the energy. And the capacitance is double energy divided by the potential difference squared. Copy this to the calculator and switch to the scientific notation. Or it is 194 picofarads. Now let's compare with the analytical solution. It is the internal layer of the dielectric, and the capacitance should be 200 picofarads. The difference is 3%. Now let's calculate the energy stored in the second layer. I will select the second layer, and here is the energy. Copy the results. This is energy 2. Capacitance, again, double energy divided by the potential difference. Copy this to the calculator. Now this is the capacitance, 130 picofarads, and the analytical solution is 133 picofarads. The difference is the same 3%. Now let's calculate the capacitance from the charge. I will start from the inside. I will switch off the cut by plane tool and hide the dielectric layer. Hide. We see internal sphere now. It is a massive conductor. It has zero electric potential, but if I switch on the color map of the electric field stress, you will see that there is some electric charge distributed along this sphere surface. To calculate the total charge, I should select the sphere surface. I switch to the integration mode and select the sphere surface, and here is the electric charge. Copy the data in the Word document again, and if I divide the electric charge by the potential difference, I will get the capacitance value, which will be 169 picofarads. Of course, both approaches should give the same capacitance value, and the difference may indicate the inaccuracy in the results. You may note that here we have not exactly the spherical surface. This surface is built from flat triangles. You might like to adjust the finite mesh spacing to get smaller triangles and better approximation to the smooth sphere's surface. But I will keep working with the existing results and show you how to measure the charge in the foil. That's simple. I will unhide the internal dielectric layer. What we have here now is the internal sphere covered with the dielectric layer and the foil. You see, this is the foil. And if I select this surface, I can calculate the charge. Please note that this charge doesn't belong to the internal capacitor. This charge is for the external dielectric layer, because we look from outside to the foil. We look from the external dielectric layer side. The charge at the external dielectric layer. And I can calculate again the capacitance, divide the charge by the potential difference, and the capacitance will be 119 picofarads. You can see there is some discrepancy between the results calculated from energy and from the charge. How to measure the foil charge that belongs to internal capacitor? That's simple. You should hide the internal dielectric layer. I will unhide all, use the cut by plane tool, hide the plane. Now you can see the electric field stress distribution. In the external dielectric layer, the electric strength changes from blue to yellow. Then we have the charged foil, and in the internal layer the strength changes from navy to orange. And if I hide the internal dielectric layer, you will see the navy color there. That is the electric field strength at the foil surface in the internal dielectric layer. And I can calculate the foil charge now. To select the foil surface, I will click the label in the tree. And here is the charge value. This is the charge of the inner dielectric layer. And the capacitance is charge divided by the potential difference is 218 picofarads. Now let's attenuate the mesh and see how it affects the results. Close the results, and in the geometry model unhide all objects, select everything and set the spacing value to 10 millimeters. Now let's build the finite element mesh on edges. on faces and in volumes. Run the analysis again. Open the results. Again, I will hide the dielectric layers. Hide. This is the internal sphere. I will use the integral tool to select the internal sphere surface, and this is the charge. It was 169 picofards. Distance is 184 picofards. You see, we are much closer to the analytical solution now than it was before. Let's measure the charge on the foil. Unhide all, hide the internal dielectric layer, and select the foil. Now you see the foil is selected and the charge is... These results were calculated when the mesh spacing were 20 millimeters, and these results are calculated when the mesh spacing is 10 millimeters. If you need better matching, better accuracy, just build more dense mesh. For example, set the spacing to be 5 millimeters. Let's see what else you can do here. You can adjust the field picture and choose different values to display. Electric potential, electric field stress. You can switch the presentation type between colored surfaces, vector plot, isosurface plot, slice plot. You can use cut by plane tool to look inside objects. And you can use the cut plane in a separate window. In this window again you can adjust the field picture, change the field quantity, switch on the isolines plot, and you can build contours here. Use the Add to Contour button to create the contour, and then you can see the field distribution along this contour in the XY plot or in the table. You can save the table in the text file, or you can copy all the data to Excel. You can copy pictures, and you can also measure local values. Just click the point and here you can see the coordinates and the field parameters. And the same you can do, of course, in the three-dimensional picture. Click and see the parameters. And you can edit the coordinates manually. On our website you can find the example page, and here you can read the description and download the simulation files.